Hey everyone, thanks so much for waiting through those technical difficulties. But we've got Dennis Way, a research staff member at IBM Research on the line. And he's going to go ahead and go through his presentation. So give me 1 second just to make sure I share his screen. Awesome. All right, Dennis, you are all set. Take it away.
All right, thanks so much, Patrick, and thank you all for bearing through that little delay, and also for joining me in these pretty difficult times. So today's talk is going to be all about taking you through examples of explaining with AI Explainability 360, or AIX 360 as we abbreviate it. So I'm going to give only the briefest of introductions to AIX 360, and then we're going to get right into the examples, which are Python notebooks, Jupyter notebooks. I'm assuming that you all are familiar with AIX 360 from the masterclass. In case that's not true, I believe it's covered in video 6 of the masterclass, so you can go back later and refer to it. All right, so before I get really started, I want to acknowledge that this toolkit is the effort of many people whose names are shown on the screen. Okay, so here's a one-page summary of AIX 360. So it currently contains 10 algorithms for explaining machine learning models, as well as data, and also 2 metrics for quantifying explainability, at least proxies for it. This was released by IBM Research. We introduced it, but we really intend for this to be an open source project. We want to build a community of both people using the toolkit, as well as those contributing new stuff to it. And it's in this spirit that I'm giving this talk today, and we're doing this masterclass and so forth. So obviously we have a GitHub repository, which probably you've all already been looking at. We have a website, we have documentation. And today I'm going to be going through 2 of what we call tutorials. So these are Jupyter notebooks, pretty detailed Jupyter notebooks that look at different use cases in different application domains. This is a taxonomy of both the algorithms in the toolkit as well as this broader space of AI explainability more generally. I'm not going to go through this taxonomy today. I'm just going to point out the handful of algorithms that I'll be covering today and roughly where they lie here. So we're going to be looking at a couple of directly interpretable algorithms that produce directly interpretable models. These are BRCG and GLRM. We're going to be looking at contrastive explanations. This is a type of local post-hoc explanation. CEM is the abbreviation. And we're also going to be looking at the proto-dash algorithm. This gives prototypical examples in either an unsupervised or a supervised context. So this is just to place these in some context. So with that, this is my cue to go right to the notebooks. I'm just going to check the conference chat to make sure there are no problems. Yeah, if you have questions, feel free to ask them through the chat. I'll try to remember to look at it periodically and answer them as we go. Okay, so let's get out of the slideshow and head over to my browser. Let me know if you've stopped seeing my screen. What I'm showing right now is our website. So this, I'm just pointing out that the tutorials I'm going to show you are linked from our website. And I'm going to be talking through two of them today. The first one is on credit approval, and the second one is this one on health and nutrition surveys. Hopefully we'll have time to go through both. So this is the first one on credit approval, and this is our longest and most detailed one. And what we do here is we look at a credit approval scenario through the lenses of three kinds of users. And we provide different kinds of explanations suited to those users using different algorithms in the toolkit. The data source for this notebook is the FICO Explainable Machine Learning Challenge. This was a challenge that happened in 2018, which incidentally we at IBM Research were the winners of. I'll talk briefly about that data set just below. So I mentioned there are three kinds of users. So the first one is a data scientist user. And this is a person who wants to understand the credit approval model globally before they do any number of things like present the model to their managers, their superiors, present it to domain experts to check that it's doing the right things, or certainly to deploy the model, right? And so for that, we're going to look at a couple of algorithms that provide directly interpretable models for that global understanding. The second user is a loan officer. So this is a person who's looking at the recommendations of the machine learning model and trying to make a final decision. For this loan officer, we'll be providing prototypes through the Protodash algorithm. These are examples from the training set that are similar to the applicant in question that hopefully can provide more context, give the loan officer more confidence. And lastly, we'll look at an actual applicant, an actual bank customer. Here we'll be looking at contrastive explanations, in particular to show how a denied applicant, what they would have to change to get their application accepted. All right, let me just check again. Are there any questions at this point? Okay, so let me jump into the data set itself. So as I mentioned, this is a data set that was provided with the FICO Explainable Machine Learning Challenge. This data set is about home equity line of credit applications. We don't really need to get into what that is right now. I will point out that this is a data set of about 10,000 actual loan applicants. And I want to point out that the target variable for this prediction task is actual outcome data. So it's whether when previous applicants, when they were given the line of credit, whether they made satisfactory repayments a 2-year period. Satisfactory meaning that they weren't late by more than 90 days. Right, so that's the target variable that we want to predict here. And we have a number of predictive variables. I think a little more than 20 variables here. I'm not going to explain them now. We'll look at some of them later in context when we look at the explanations that are provided by the algorithms. I just want to point out that at the moment that FICO has been helpful in providing not only a data dictionary, but also an indication of whether these predictors should have an increasing or decreasing relationship with the target variable. The target variable is, it has been binarized into just two labels, good and bad. So good means that the applicant made timely repayments. Bad means that they were late for more than 90 days on at least one payment. Yeah, so I think that that's all I want to say about the data at the moment. So with that, let me, okay, there's one more thing I want to say here, which is that if you would like to play with this Python notebook later yourselves, it does require you to get the FICO data separately. For legal reasons and other reasons, we are not providing the data as part of the repository, the GitHub repository. There are instructions on how to go to the FICO web and get it yourself. You have to fill out a form, and then a link will be emailed to you. And once you get the file, there are instructions that are repeated here on where to put it within your local file structure, so that you get access, so that it gets recognized. Okay, so let's go to the first type of user, which, as I said, is a data scientist. So this data scientist wants a global understanding of the machine learning model that was built for this credit approval task. I mentioned a couple of reasons why they might want this. They have to present this to their superiors. They want to confer with a domain expert, a lending expert, to compare notes, right? See what the model is, how the model is making recommendations. Experts, or they might have to present it to a regulator to check for compliance. Any number of reasons why you might want a global understanding. So for this purpose, we're going to be producing directly interpretable models. And what directly interpretable means is that the model itself has a sufficiently simple form to be transparent, to be understood. Right? That understanding might not come at a glance, but with some study, right, by human beings, it can be understood. And we're going to look at two algorithms that produce these directly interpretable models. One goes under the acronym of BRCG, Boolean Rule Column Generation. And then the other one is GLRM, that stands for Generalized Linear Rule Models. I won't say exactly, I won't explain all the words in that acronym, but we'll see by example what kinds of models these produce. Okay. So the first step here is we have to actually load the FICO data. So I'm going to more or less run this in real time as we go through this, right, to show you how it goes. So we're loading the FICO data. I want to point out that AIX 360 provides some data set classes to help you with this. So we're invoking the HELOC dataset class here to do that. And I'm calling it with a particular pre-processing option. We've called it NAN pre-processing. And among other things, what this does is the original data set, it contains some special values that are notated with negative numbers. This NAN pre-processing, it converts most of them to the NumPy NAN representation. And if we look below, we can see some examples of, here's a NAN, here's another one, right? And we're preserving these, special values or missing data because these two particular algorithms, BRCG and GLRM, they can handle them properly. We don't need to impute them with, zeros or the mean value or anything like that. So we're going to keep them as is. And then the other thing we're doing is just the standard splitting the data into a train and test set. Right? So that's all that has happened. Okay, so then the next thing we have to do with this data, we can take a glimpse at some of the feature values here too. So as I said, there are, I think, 23 features. They're all numerical, aside from these NaN values, as you can kind of see. So the first thing we actually have to do for these two algorithms is that they take binary features as inputs. Right, so we have to take these continuous valued features and actually binarize them. If you run any type of tree-based model, like a random forest or a decision tree or a gradient boosted tree, implicitly this kind of binarization or discretization is happening. It's just that with these two algorithms in AIX 360, we have to do this binarization explicitly. So again, in AIX 360, we provide a feature binarizer class to do this for you. So that's this one here, feature binarizer. And I'm calling it, I'll explain this later flag, the return ORD flag later. Here I'm just instantiating feature binarizer, calling fit transform on my training data, and then similarly transforming the test data. This is most easily explained by just showing you, an example of what it produces. So this was the first feature, something called external risk estimate. And here it has been, as you can see, discretized using a number of thresholds. Right, so you can bear with my scrolling. You can see that the first applicant here, ID 8960, this person had an external risk estimate of 64. Okay. And that in this binarized representation is represented as follows. So we're comparing against a set of thresholds, 59, 63, 66. So 64 is less than 66, but it's not less than 63. Right. So you see there are a couple of zeros and then ones thereafter in the less than or equal to columns. We also have the greater than columns, which are complementary. So these are the negations of these less than or equal to columns. And as you expect, it's just the complement. Right? So this is what feature binarizer does. And it does this for all of the 20 odd numerical features. Okay. Okay, let me go on then. So now that the data has been prepared, we're going to run the first algorithm, which is BRCG. What this produces is what is known colloquially as an OR of ANDs model. The more formal term is a DNF, a disjunctive normal form. Let's see, what else do I want to say here? We do have a paper on this, of which I am an author. So if you really want the technical mathematical details, I'd refer you there. I'm not going to say too much more about how the algorithm actually works, but I'm just going to show you what it does. So here in this code snippets, we're instantiating a Boolean rule classifier with certain parameter values. I'll talk about those just in a bit. Let me get this running first because it's going to run in real time and it takes a little bit of time. So while that's running, let me explain what we're doing here. So we are actually learning an OR of ANDs model for the bad outcome, right? So we're giving a set of reasons for why people might be considered bad credit risks. And these lambda 0, lambda 1 parameters that were used to instantiate the model, these were selected ahead of time to provide a good trade-off between the accuracy of these rules and their complexity. Right? So with many of these directly interpretable methods, you have a trade-off between how complex your model is, in this case, how many rules it contains and how long they are. So how complex the model is and how accurate they are in predicting the outcome. And these parameters, as I said, were chosen to give a reasonable trade-off in that regard. If you come back to this notebook later, these parameter values are something that you could play with to get either less or more complex models. I'm not going to do that here in the interest of time. So I think this should be about done. And when it's done, it will print out the rules. Okay, so here we go. So training accuracy is about 71.9, 72%. Test accuracy is just under 70%. Right? Just keep those numbers in mind as a rough ballpark for what we should expect on this data set. Around 70, low 70s. And these are the two rules that it has come up with for predicting y equals 0. So that's the bad credit risk label, right? So it says either, let me interpret it a different way. So number of satisfactory trades. Think of this as roughly the number of accounts or credit agreements that you have, that a customer has, right? So if you have a credit card or if you have a car loan, right, each of these would be considered a trade. And satisfactory just means that you've made at least one on-time payment for this credit agreement. So if the customer has fewer than 17 of these satisfactory trades, then we require the external risk estimate to be less than 75, or yes. Whereas if they had more than 17 of these satisfactory trades, then this threshold is a bit lower. So this external risk estimate feature, it's pretty important, I have to explain. So think of this as like a consolidated risk score, and higher values in this case are better, right? So intuitively, what this set of rules is saying is that if you don't have too many accounts, if you don't have too many satisfactory trades, I'm sorry, the other way around. So if you don't have too many satisfactory trades, then we want to see a slightly higher external risk estimate, slightly better risk score than if you have more accounts, right? And that makes some sense in that the more accounts you have, generally, lenders regard you as having more experience in dealing with credit, and so the requirement is slightly relaxed. So, aside from interpreting this, we see that BRCG gives us a really simple rule set that, and as we'll see later, this accuracy is already, it's not the best, but it is already pretty good, right? It gets us most of the way there, and we didn't have to, invoke any complicated logic to get that understanding. Yeah, so I think that's what I want to say about this first algorithm. Let me again check the chat. I don't see any questions at the moment, so I'll keep going. Yeah. Okay, so as I said, this very simple rule set gives us decent accuracy already, but in most cases, we want to do a little better, right? We want to get slightly higher accuracy, and this will cost us in terms of needing a more complicated model. But the one that we're going to see next is still, it is still directly interpretable in that it can be studied by human beings and understood. Right? It is not an opaque neural network, for example. Okay, so the next algorithm that we're going to look at is called GLRM, and specifically it's a logistic regression variant of GLRM. Logistic regression because our output is binary in this case. So this is, it's also a rule-based model. But the way the rules are combined is through linear combination. So it's a combination of a linear model and rules. And that may not mean very much at the moment. We'll see exactly what kind of model this produces after this runs. So the code to invoke it is very, very similar. We're going to instantiate logistic rule regression, again with some complexity parameters that provide a good trade-off between rule accuracy, model accuracy, and the complexity of the model. So here again, we're calling fitting on the training data, and then we're going to score it both on the training and the test data. And then this explain method that I'm calling at the end, it's already finished, right, is going to print out the whole model. Okay, so if we look at the test accuracy here, we see that it is, slightly but significantly better than the one from BRCG. So we get 72.6% test accuracy, and this is basically a logistic regression model, right? So it's a generalized linear model, except that the features that it's using are not just the raw features, but they are these rule-based ones. So here we have the full table of all 36 features that this logistic regression model is using. Now, if we had a couple hours and our jobs depended on understanding all these features, we would go through these one by one. I'm not going to do that here. We're going to see shortly a better way of summarizing this information. But for now, I want to make a few comments. So let's see here. Right, okay, so the first one is that, as I mentioned, this logistic regression model uses rule-based features. And the way to see them in this table is, for example, if we look at this number 1 here, right? The rule-based features all involve comparisons, right? So this one says that this month since most recent inquiry, excluding 7 days, it's a mouthful, I know, but that feature is greater than 0, right? So if a person has this value greater than 0, then this rule-based feature gets a value of 1. And if this comparison is not true, they get a value of 0, right? So these are exactly the binarized features that were produced by Feature Binarizer. If I quickly scroll back up here, right, flashing this binary matrix, right, these are the features that we're talking about. So these are the rule-based features, but the original features also make an appearance. So for example, this next one here, number 2 is external risk estimate. That's the consolidated risk score that I already explained. And this one is appearing, without any comparison. So it's appearing in its original numeric form, right? So the fact that it's number 2 on this list, this is a ranked list sorted by the size of the weights, the model weights. This indicates that this external risk estimate feature is pretty important, which we knew already from the BRCG output. Okay, so we have rule-based features, we have original features. That's one point I want to make. The other point is, and again, you'll have to trust me on this, none of the rule-based features here actually create interactions. And so what I mean by that is, if you look at these conditions, they're all conditions on single features, right? We don't have, say, number of revolving trades with balance less than 5 and something else, right? They're all single conditions. And that happens to be a quirk of this data set. But it also means that we can easily visualize the effects of these features. And, for example, if we look at external risk estimate again, we see it appears in position number 2 in its original numerical form, but it also reappears several times later. Like in number 14, for example, we have a threshold rule on it. It appears again in number 23, right? So it appears multiple times. And rather than having to kind of stare at this table and try to make sense of this, we can actually plot the results. So that's what I'm going to show you next. Let me just check again the chat. Okay. All right. So if you're interested, this model that we've produced is actually an instance of what is called a generalized additive model. I'm not going to explain exactly what that means here, but it does help us visualize the model. And as I mentioned, right, we have this table of 36 features, but you see that some of them involve the same original features. And in fact, there are only 14 of the original features among these 36. So this little segment of code is just counting that number. We get 15 because the intercept, the constant term, is also counted. So, as I said, we can use plots to help visualize the model. And what these plots show are the dependencies of the model on each of these 14 original features, right, that were contained in that table of 36. And the model as a whole, because it's linear, because it's additive, it's just going to be the sum of these one-dimensional plots that I'm going to show you, right? So this, you might be familiar with things like individual conditional expectation plots, ICE plots, or partial dependence plots. These are like those, except that, for a general model, a partial dependence plot depends on where in the feature space you are, right? The dependence on the variables can change depending on which data point you look at. For this additive model that we're looking at, that's not true, right? It's the same partial dependence no matter where you are in the feature space. So that means it's easier to understand, and that the same dependencies hold for everybody. So let me show you some examples of these. I don't think I'm going to go through all of them. So here, for example, is the component of the model that depends on this external risk estimate feature that I've already said a few things about, right? So on the x-axis is external risk estimates, or ranges in values from 30 to almost 100. And on the y-axis is plotted the, if you want to get technical, it's the contribution to the log odds of the positive outcome. So in short, just think of higher values as better credit risks, right? In this plot, right? So as I promised you, this external risk estimate, it's positively correlated with being a good credit risk. So higher values are better. That's the general linear trend that we see. In addition, there's some nonlinearity going on, right? It takes some jumps. Those are due to the rules in the model. It takes some jumps in the 70 to 80 range. So, you could interpret this as saying that, in general, a higher external risk estimate is better, But if you can get over this kind of 70 region, right, you get an especially large boost in your score, right? It's the people with scores, say 75 and above are noticeably better than the ones with scores 70 and below. We can look at another one. This is another one that I mentioned. So months since most recent inquiry, excluding the 7 days, the past 7 days. So credit inquiries are, things that lenders do, or sometimes employers or landlords do, right, to check your credit when you want to apply for something. If you have too many of such inquiries, it kind of indicates that you're making too many applications because you are perhaps desperate for credit, right? So having, too short an interval from your last credit inquiry is not a good thing, as some of you may know. So this, for example, shows something kind of interesting in that as long as your month since most recent inquiry is 1 or greater, so as long as it has been a month since your last inquiry, then it kind of doesn't matter, right? But if it was less than a month, then you take some penalty in terms of what the model is predicting. Yeah, so there are many others that you can go through here. Again, in the interest of time, I think I'm going to skip most of these. So this one, for example, again, shows that the more inquiries that are made in the last 6 months, the worse the model thinks you are in terms of credit risk. Right. So all of these are in accordance with domain knowledge. Okay. So I think that will do it for this first data scientist persona and these algorithms that produce directly interpretable models. I'm going to switch gears to a different one. Yeah. Okay. So the next one, the next thing we're going to look at is a loan officer. By the way, maybe Patrick can answer this. Are we still going until the top of the hour, or until 10 minutes afterward? You can answer this question in the chat. 10 minutes after is fine. Okay, good. Okay, so the next user we're going to look at is this loan officer. And as I said earlier, we're going to provide prototypical explanations for this loan officer. So this loan officer is seeing actual applicants, what the machine learning model is predicting for them, and we're going to provide prototypes from the training data that are similar to the applicant in question and have the same prediction, so that the loan officer can understand this applicant in context, see how they might be similar to ones that were approved or rejected in the past, and thus be able to make their final decision more confidently. Right. So we're envisioning a scenario where the machine learning model itself is perhaps not making the final decision, but it is still passing through a human loan officer. So for this, we're going to illustrate the ProtoDash algorithm in AIX 360. Yeah, so let's just get into it. So you have to do some reloading and preliminary stuff again. This Python notebook was designed to be run independently, right? So you can run these sections independently of each other. That's why there's some somewhat redundant stuff going on here, right? So we're just importing a bunch of things. We're going to reload the FICO data sets, but in this case, so we're again calling that HELOC datasets class. In this case, we're not going to use the NaN preprocessing option that we used before. I believe we're going to impute those special values. I don't remember exactly how they were imputed, but we're going to be using a neural network later, so they need to be imputed with something numerical. So that's what's going on here. Here again is a snapshot of the data, the first 10 applicants. You can even see some of these special values, like here is a -8, for example. Yeah. You can also look at a histogram of some of the features. These are some features that we've talked about already: external risk estimates and number of satisfactory trades. Right. Okay. So again, we're going to be doing some pre-processing, so splitting the data into training and test sets. This segment just normalizes the data. So as you can see, the comment here says we're going to normalize values to within the interval -0.5 to +0.5. Okay. Now we're actually going to train a neural network to again predict this same repayment outcome. It's a fairly small one, a 2-layer one with not too many hidden nodes. And in fact, we're not going to do this in real time. I happen to have the model already saved on my machine. So this is just going to load it from memory. And right, and it's going to evaluate the model accuracy on both the training and test sets. I'm going over this stuff quickly because it's standard stuff. So at the bottom we see the training accuracy and test accuracy. Test accuracy is 72.2%. So again, in that same low 70s range. And in fact, for this data set, it's not better than the directly interpretable rule-based model that we saw earlier from GLRM. Right? So interpret that how you may. Okay, so what are we going to do with this? We're going to look at a couple of applicants, so a couple of rows in the test set. This first example is someone who the model predicted as a good credit risk. Right, so the prototypes are going to be drawn from the training data, and in particular those training points that were also predicted as good. So this few lines of code they are just extracting those training instances that were also predicted as good, so we can search through them. Okay, so this particular applicant who was predicted as good, their index is 8. This, I believe, will just print their feature values and also their predicted probabilities. Okay, so here we see the prediction was good. These are the probabilities. I don't know why this number is less than 0, but perhaps this wasn't properly normalized. But in any case, this number for the y=1 label, the good label, is higher than the one for the bad label. Right? So this is a good candidate, and here are their feature values. Yeah. So now we're going to find applicants in the training sets that were also classified as good and are similar to this applicant in terms of their feature values. So for that, we're going to use the protodash algorithm. So here we instantiate protodash, and we're going to call its explain method. So X is this applicant in question. Z train good, that's the part of the training data set that was classified as good. And M=5 here means that we want to return 5 prototypes, 5 applicants that are similar. So let's run this. And now we're going to display the results. So here they are. So here are the 5 prototypes, 0 through 4. Here are their feature values. And, at the bottom here, we have also computed a weight. These are numbers indicating how similar these applicants are to that applicant number 8 in question. Right? So if you can read these small numbers, this first applicant, this first column here, is by far the most similar person. Right? And the others are a lot less similar. In addition to this, we can also look at, if we had a lot of time, we could obviously stare at these features and understand them. For something quicker, we can look at basically which features are exactly identical to the applicant or very close. So in this table that I'm showing now, if you see a value of 1, that means that this person's feature value is exactly the same as that applicant number 8. So just looking at this column number 0, we see a lot of 1s, and that just means this person had identical values for a lot of the features, right? So that's confirms that they should be most similar. Yeah, I don't think I want to make more specific comments on this in the time that I have. So let's go on for the moment. We can also look at an example of somebody who was predicted as bad. And again, we're going to be finding prototypes from the training set. This time, we're going to limit to those training points that were also classified as bad. Right? So this, in many ways, is a repeat of what we just did for the good case. Yeah, so I'm just going to quickly run through this. Right. Okay. I remember the comment I wanted to make here. So, if you have studied this, like I have before giving this talk, so again, we return a set of prototypes that are similar to the applicants in question. Again, the first column is the most similar person. And if you've studied this ahead of time, like I have, the thing that jumped out to me was the relatively high debt burdens of these people. So that's reflected in these 2 rows that I'm highlighting here. These are, some of these are very high values, like 232. So a loan officer with a lot more domain expertise than me, right, might look at that and, kind of mentally classify this person as having a high debt burden, like these other applicants who had a bad outcome. Okay. So I think that's what I want to say about the loan officer. Yeah. So that was the second user that we illustrate through this Jupyter notebook. Let me go now to the third one in the time that I have remaining. So this is a customer user, customer persona, meaning a person who is actually making an application for this line of credits and is either approved or denied. And most typically, we think that the people who most wanted explanation from the machine learning model are those whose applications were denied. And they would like to know, in particular, kind of what were the features that were most important in their decision and how they could be changed to give them a positive outcome. Right. So that's what the contrastive explanations method can do. It's abbreviated CEM in the toolkit. Right. So, as it says here, it tells applicants, what are the minimal changes to their profile they can make to change the decision, presumably from deny to approve. It also can highlight, this first set of changes is called the set of pertinent negatives, for reasons that I won't get into now. Again, there are papers behind all of these algorithms, which you can study if you're really interested in them. The second thing that this contrastive explanations method provides is it also can highlight a minimal set of features that are sufficient, meaning that these are kind of the minimum necessary to preserve your current prediction. And these are called pertinent positives. So we'll be seeing examples of both of these, and hopefully what these mean will become a bit more clear. Right, so let's get to it. We're going to be actually using the same neural network that was used for the loan officer example, and that's because this contrastive explanations model method, it's what is called a post-hoc explanation, right? So that means that you already have a model that is providing the predictions. It's most likely a black box, and you're using a secondary method to provide explanations, right? That's what's called post-hoc, and we're using the contrastive explanations method in particular to do that, to give those post-hoc explanations. So with that said, this, getting the neural network model it's running the same code as before. So let me just do this so that we have the variables instantiated. So this is exactly the same thing that we did for the loan officer. As you see, the test accuracy is still that 72.2%. Okay, so now we come to the interesting parts. So now we're going to generate contrastive explanations for two applicants. The first one is one whose application was denied. And this one we're going to give pertinent negatives. In other words, what this applicant would have to change, the minimum set of changes they would have to make to get their application approved. So this person's ID number is 1272. Right. So I think this actually launches it. So let me explain a little bit of what's going on here. So X is pulling out the features of the person in question, of the applicant in question. We're going to invoke the CEM explainer. Again, CEM stands for contrastive explanations method. We're going to put it in mode pertinent negatives, right? We're finding the pertinent negatives, the things that have to be changed. See, anything else worth? I mean, it requires you setting a bunch of parameters like basically any algorithm. I might point out one here, which is this beta parameter. This controls, like I've been saying, minimum set of changes, right? And this beta parameter kind of controls what minimum really means, like how many features have to be changed and by what amounts. And by tuning this beta parameter, you can make that set larger or smaller and the changes larger or smaller. If you're mathematically inclined, this controls an L1 norm of the changes. So we're going to call explainer, the explain instance method of CEM with the data point in question and all of those parameter settings. It is already run in the background while I was speaking. So now we can look at the results. So this code is basically just to show the results. Okay, so here is the summary that we get. So here is the original prediction, right? This was a bad credit risk prediction. The number for the y=0 label is higher than the one for y=1. Again, disregard the fact that we have negative probabilities here. And then here is the pertinent negative version of that same applicant, right? So this is the hypothetical applicant whose values were changed so that now we get a good prediction with a certain margin. And this table shows the original feature values, the hypothetical ones that would be needed to get a good prediction, and the differences, right? And as promised, the changes, the algorithm tried to make the changes minimum, right? So only 3 of the features have to be changed. For example, the external risk estimates, right? That risk score that I've been talking about a lot. This has to be increased by 11.4 points. This one is average months in file, so that's kind of your average credit history length. We need to add 12 months, about a year to that. And the number of satisfactory trades also has to increase, right? So this is a small set of, you can view this as a small set of recommendations that is made to the applicant to improve their profile. We can also compute a relative importance of these changes, and that's what this bar graph is showing. Let's also look at a pertinent positive example. So these are the minimum set. These pertinent positives are the minimal set that is sufficient to maintain a prediction. So for this case, we're going to look at somebody who was already predicted as a good credit risk. They got the good label. So this code for calling CEM is basically the same as before, except now we've changed the mode to pertinent positives. So let me run that and then show you the results. Okay, so I think that's done. All right, so this is printing out the results again in the same format. So this was applicant number 8 again. This is an applicant that we already looked at, in fact. The original prediction was good. And this table explains what I mean by pertinent positives. Right? So these are kind of the minimum values that this applicant would have to retain to continue to be classified as good. So as you can see, their external risk estimate in this case could decrease by a lot. Surprisingly, a surprising amount, I have to say. Their average months in file could also decrease. Their number of satisfactory trades could also decrease. Where you have zeros here doesn't actually mean that the values can decrease to 0. It just means that there is no change to the original features. So this gives an indication of kind of the minimum requirements, for this person to still be approved. And again, we can show a bar graph of the relative importances of these 3 features. All right, so I think I'm at time, even with the 10 minutes delay that we have. So I unfortunately don't have time to cover this second Jupyter notebook on a health and nutrition survey. This is looking at, I'll just briefly say that this is looking at some survey data from the US CDC, Centers for Disease Control and Prevention. And it's using the proto-dash algorithm, which I already talked about, in an unsupervised manner to try to better understand these survey data sets and how one survey might relate to another. The finding here is that a survey on people's incomes relates most closely to a survey on people's childhood experiences, which is pretty interesting. So I encourage you to look into this more. And again, these are all linked from our website here, right? So it's the Health and Nutrition Survey one. So with that, I'll stop. And if you have any questions through the chat, let me know and I'll try to answer them. Thank you. So I see one comment that might be a question. Says the result, it's from Srinivasan, the result is same as the metric we do for machine learning. How is this different from explainability model outcome? I have to confess, I don't quite understand. There's another question on, are these notebooks part of the AIX 360 on GitHub? That's an easy one to answer. Yes, they are. And I can show you. So they, in addition to being directly linked from our website here, they live in the examples folder. So this is the AIX 360 repository. If you go to the examples folder, we have a lot of examples. The more complicated one, the more detailed, complicated ones are under this tutorials folder. So, for example, the one that I went through is called HELOC, right, for home equity line of credit. The one that I didn't have time to cover is called CDC. And there are some less complicated ones that are just illustrating, how to use the different algorithms. Like, for example, here are some ones showing you how to use CEM on the MNIST digits data set. So you can find a lot of examples here. Okay. So there's a question from Amin. We generate model and it produces 72% accuracy on test sets. And then we build an explanation on top of that. How much can we trust the explainability model? This is a good question. And it depends, I would say, first on whether you're using a directly interpretable model or a post-hoc explanation of another model. Right? In the case of a directly interpretable one, I would say yes, you can trust that the explanation you're getting is faithful to the model because there is only one model and it's directly explainable, right? So it is what you're seeing is in fact what it's doing. In the post-hoc case, we do have to distinguish between. There is a difference between methods that approximate the original model to some extent and ones that don't. So, for example, you've probably heard of LIME. I forget exactly what it stands for. I think something like locally agnostic model explanations, right? This is a method that fits, so it's a local method, right? So given a test point, you fit a linear model locally to the black box model that you are trying to explain, right? So inherent in that is there's going to be some approximation error because that linear model cannot describe fully the behavior of the original model, even in the local neighborhood, right? So in the case of LIME, there may be a mismatch between the models, and thus, a problem with the fidelity of the explanation. With the contrastive explanations method that I presented to you, CEM, there is less of this problem because the perturbations that CEM is making to the model, like, for example, these pertinent negatives that were required to change the predicted label, these are actually fed through the black box model, right? So there is a guarantee that if you change these values in the way prescribed here, right, then your model output will change, right? So there is that fidelity question to be aware of, right? Of course, trust is a much larger topic, involves non-technical things, non-technical issues too, which I can't really address here. And then you further commented to explain there was a level of generalization, correct? Yes, I guess that's true at a high level. Whether that generalization is approximating your original black box model, or some other simplification to allow us human beings to understand what is going on. Right? So there's always that issue. And for a directly interpretable model, the issue might be that the model is, while it's simple enough for us to understand, it might not be complex enough to capture everything that's going on and get the highest possible accuracy. Right. So these are trade-offs that you often have to make.
Awesome. So if there are no more questions, I think we can conclude today's webinar. But guys, if you have any questions that come after this, or you're watching this replay and you want to follow up with something and get a question to Dennis, feel free to go to the questions tab and post it there. And one of our mentors or admins will see it and follow up with him. But yeah, appreciate your time, Dennis. And thanks everyone for joining.
All right. Thank you all so much. And Thanks for bearing with me too through the technical delay.
Thanks, everyone. Have a great weekend.
Bye.